All right, so welcome back. Today we're gonna talk about a couple algorithms. I think I'm gonna divide this into multiple videos, part one, part two, part three, because this is quite long. So last lecture, I think we went over the Mercer's theorem. Today we're gonna talk about Nystrom, random Fourier feature, and why random Fourier feature could be really useful. Okay, so this is Professor Wu, Northeastern University. So last time I think we started talking about Mercer's theorem, and one of the key takeaway as a result of Mercer's theorem is that previously we had to use feature maps, right? And the feature maps are based on basis functions, and depending on how many basis functions, then you have to plug x into every one of them. For certain kernels, you end up having infinite basis functions. As a result, it's just not really possible for you to essentially use it as a feature map because, well, the dimension is infinity. What we discover from the Mercer theorem is that instead of using the basis, the same kernel function could be achieved when you use a different set of bases, specifically when you use the eigenfunctions. And when you use the eigenfunctions, instead of infinite of them, very often you can approximate it using a finite number of them. So instead of infinite, just m of them. Therefore, you can use, instead of phi of x, you can use an approximate version called phi hat of x. And when you do phi hat of x transpose phi hat of x, right, this is basically the same as the kernel function itself. Okay, so this right here tells you that instead of using infinite dimension, right, you can use finite dimension. Moreover, we also learned that essentially once you have this idea in mind, then when you want to map the data x to phi of x, you can just map it to phi hat of x. And the phi hat of x is equal to here v sigma 1 half. Okay. So what is V? The columns of V are the eigenvectors of the kernel matrix. And these are the eigenvalues. Okay. So you want to refer back to the previous lecture if you don't remember. So the advantages, this matrix here was n by infinity, whereas this matrix here is n by m. So this is possible, while n by infinity is obviously not possible. Right, so that's a really key implication. Now, previously, if we have an algorithm, like you're trying to minimize something like this, we would have had to, when we want to convert to kernels, we would put all the x and convert it into phi of x, right? And then we would somehow manipulate the algorithm so that all these phi of x disappear through the kernel trick. And as a result, you end up using a kernel matrix instead of using phi. However, for those algorithms, we got lucky. There was a way for us to create the kernel matrix. Very often, there are algorithms you cannot create a kernel matrix. And if you can't create a kernel matrix, you are stuck with potentially infinite dimensions. Well, using Mercer's theorem, instead of x to phi, you can simply use phi hat. And therefore, this is no longer infinite dimension. So each row of this matrix is simply the ith sample in RKHS. And therefore, since this is finite, we can now plug this in. And therefore, we can solve many, many problems that would have otherwise been impossible and make that possible. Okay, so that's basically the key takeaway. It makes a lot of algorithms much easier because you don't need to do the kernel trick anymore. Okay? All right. So as the first exercise, I want you to see if you can reproduce the Mercer theorem. So for the Mercer theorem, the idea is that you can get the feature maps this way. Right. So what I want you to do is I want you to generate 10 random samples of two dimension. Once you generate that, then you can generate the K matrix using sklearn. So this will be the true kernel. And over here, This is how you can approximate it through the Mercer's theorem, the phi hat matrix. Once you approximate this, right, using I don't know how many eigenvectors you want to use, you can calculate the kernel matrix. This kernel matrix and the true kernel matrix should be similar, very close to each other. Okay, so that's the first exercise, and I think, I want you should definitely go and take a look. Okay, so I post the solution here as well. Essentially over here, this is the true if you just calculate the kernel matrix element by element. And this one is the approximate kernel matrix. Notice how I just created phi. This is our phi hat matrix. And it's equal to the eigenvectors of the kernel times the eigenvalues. And notice how the two matrices are basically identical with each other. Okay, so that's going to be part one of this video. In next part, I'll move on to Nystrom. Okay.